Okay, we're going to do a quick goodness of fit problem. This is in section 11.2, number 9. The reason I picked this one is because, well, it's getting a little more cumbersome to calculate the chi-squared statistic when we get this many categories and the numbers are getting large. And this also talks about this Benford's law a little bit. So it's a good one for us to go through, and I'm going to show you how to do it on StatCrunch. So we've got this data here, and this is the idea that the leading digit or leading digits should fit a certain type of frequency. And according to this Benford's law, we should have like 30% of the leading digits should be a 1, 17.6% should be 2, 12.5%. So those add up to 100%. Now what's interesting is we've got sometimes the frequency or the expected frequencies are below 5. And Benford's law says if we can find one or more of the categories that are kind of freaky or weird, then we can reject the null. So that's not a huge deal right now, but I'm just going to go ahead and load this in StatCrunch. And when we're doing our chi-squared statistic, it's observed minus expected squared divided by expected. And what they do here is, here's the actual frequencies. So this is what we'd call our observed. But we don't know the expected, but we do know the expected percentage. So the first thing I need to do is, how many occurrences were there? So I'm going to let StatCrunch do this. So if we go to Data, Compute Expression, and I just hit Build, if I type the word sum, open parenthesis, and I just do actual frequency and hit Add, and then close that and compute, and hit OK, compute. So there's 774 occurrences. It just added up all the frequencies. So, I mean, you can type that in your calculator, but if you know how to do it, StatCrunch saves you time, especially if there's a huge list. Okay? But that still isn't exactly what I need. I need to know how many are expected. So, for instance, I need to know that 30.1% of 774 is the expected value. So really, I want to take 774 times every one of these percentages. Now I could do that on my calculator, but I'm going to tell StatCrunch to do that. So I'm going to go Data again, Compute Expression, Build. So what I'm going to do is take 774 times the actual frequencies, but that, times Benford's law is what I'm going to do. That's the percentages. So I'm going to take each one of the percentages times 774, but I don't want 30. I want 0.30. So then I'm just going to divide by 100. So that makes it a percentage. Instead of 30.1, that makes it 30.301. And I'm going to hit OK and compute. So there they are. There's all the expected values. So really it just took 774 times 0.3, 774 times 0.17, and there they are. So now here's our observed, and here's our expected. If we want to do this by hand, we would just take observed minus expected, divided by, and square that difference, divided by expected, and then add them up. But StatCrunch can do this for us as well. So if we go under Stat, and we are doing a goodness of fit, and we're doing a chi-squared test. The observed are in the actual, the expected are in this big calculation column we did, and I just hit compute. And there it is. We got a humongous chi-squared statistic of 3,836, which is stupid large, okay? And the probability of getting that is essentially less than nothing, really 0. And if we want to, just for fun, take a look at our chi-squared table, since we have 9 categories, that's 8 degrees of freedom. If we look in row 8, look at, even at the 0.005, way out here, you need a chi-squared of bigger than only 22, and we got 3,000 something, okay? Which means we have very strong evidence that this data does not fit. In fact, we have, and all you really need is at least 1 to say this, and we definitely have that. So let's go back to here. And so you could say there's the chi-squared, the p-value. We're going to reject the null. There is significant evidence to warrant rejection of the claim that the leading digits are from that distribution of Benford's law. It does not appear, and these are like fraudulent checks, like how many checks should start with a 1, a 2, a 3 when you're writing checks. It's kind of interesting. They've actually researched this. So that's pretty much it. And that's going to help you do, you can all of them do this way, but I would also suggest making sure you understand this formula here, just the raw one, the chi-squared equals the sum of O, which is observed minus expected, squared divided by expected, and then we add all those up. So here's the notes. I would suggest looking at those and getting a few more examples.